Hello and welcome to the HyperCrash for LS-DYNA webinar. Today I'm going to show some of the most important features for the usage of LS-DYNA models within HyperCrash. We will have a look at the graphical user interface. We will see how loads and boundary conditions can be defined. We will look at contacts. We will look at penetrations. We will look at include files, transformations, parameters, model checks, safety tools, and finally a combination with meshing and HyperMesh. So first of all, let me give you a little bit of historic information about HyperCrash. HyperCrash was developed together with Radios, with explicit code Radios, and the preprocessor was formerly called mCrash from the company called Mechalog. It was incorporated in HyperWorks with version 8.0, and you see that the graphical user interface looked very different than it looks today. A lot of different icons, different mouse settings, and so on. In HyperWorks 9.0, it was adapted to the HyperWorks to the other HyperWorks products. The icons were adapted, and also mouse settings were adapted. And starting with version 10.0, we had a complete LS-DYNA interface. And also the interface, the graphical user interface looks a little bit different. We have a model browser and so on. Everything looks more and more like HyperMesh, HyperView, and can be used as all the other HyperWorks tools. Right now we're working with HyperWorks 11.0, update 4.02. The LS-DYNA interface becomes more and more complete. Of course, not each and every keyword can be incorporated as soon as it is as soon as it is found in LS-DYNA, but we try to keep track, and please let us know if you need a keyword. Then we will put that into the preprocessor as well as soon as possible. Where can we find HyperCrash? HyperCrash can be found in the complete package of HyperWorks 11.0. We find HyperCrash over here. As soon as we open HyperCrash, we get a small GUI which asks us for the working directory, for the user profile, and for the unit system that we want to use. There are different interface styles. Of course, we use the new one. You can still work with the classic one for users that are used to this classic user interface, but we will start HyperCrash with this new interface style. HyperCrash comes up. You see we have a graphic area, we have a tree area, browser area on the left side. We have some pull-down menus and also some shortcut icons up here. We start to import an LS-DYNA model. LS-DYNA Explorer with include files. You see there's this master file and several include files in this directory, and it can be read into HyperCrash without any problem. You see on the left side we have a tree browser where we can find all the different parts. We have the graphic area where we can play around with the model, rotate, scale, and so on. We can change the style of the visualization, for example, shade with lines. We can change the style for the rotation. So during rotation, it should look the same. It's very easy to to switch on and switch off several parts, turn them on again, switch them off again, find several parts with a pre-highlighting, and this makes it very easy to work with a model and makes it very easy to work with a visualization. If we want to find one of these parts, for example, the window, we can say show selected part in tree. We can look at this part and we find it immediately in the tree file. We can, of course, isolate this part or look at this part with transparency. Control transparency, we can look at that part in detail and see where this part is located within the whole structure. Of course, we not only have this tree browser, we have a complete model browser over here, where we can not only look at the single parts, but also look at boundary conditions and load cases. For example, we can look at the initial velocity that is defined here. If we switch these on, we see that there's initial velocity defined for the whole car, for example. We can look at the rigid wall, for example. We see that there's a rigid wall defined for the floor, and the normal direction is in Z direction. And we can see the different include files. In this case, we can have a different view with includes, and you see that now within these include files we have several parts, and for example, we can look at the frame and isolate them, for example, to see only the frame parts. This is very easy in this case. Can be done very easy. What else do we have? We can look at the whole car again, display the whole car again, and of course we can make settings for material, for property, and for parts. The most important connection: part, material, and property over here. Let's, for example, look at one of these parts. If we review this part, then only this single part is displayed, and we have access to all the information that's available for this part. For example, material, property, and all the other parameters that we need here. If we are interested in the material that is used here, we can edit this material. We become all the information for this material, ID, density, Young's modulus, and so on. And finally, we see the load curve that is used over here. We can edit this load curve and define the material information directly over here. Or we can import a curve over here, define some scale factors, whatever we want to do. At the same time, of course, we can look at the property, edit the property, and we have access to all parameters that are available for LS-DYNA. For example, different element formulations over here. We can use different number of integration points, and so on. All information is available here. What else can we do? Of course, we can define loads and boundary conditions for the car. We've seen that we have one rigid wall for the floor. Let me give you an example for another boundary condition. Let me just define another rigid wall for example, for a pole crash test from the side. So as I said before, rigid wall planar. This is the rigid wall that was already defined. Let's define another rigid wall, and this time we define a rigid wall geometric cylinder for the pole crash. And we can first of all define the position of this cylinder. There are different possibilities how to define this cylinder. For example, we have to define the coordinates over here, and we can define the coordinates by picking a node, for example. So the pole should be located somewhere over here, and we have some first idea for the coordinates, where these coordinates should be located. So I will change this coordinates a little bit, 2,300. Then let's put it y coordinate to 1,100 and 2,000 over here in z direction to make the head of the coordinate vector up here. Then the same over here, minus 2,300, 1,100. And then we will direct the normal vector upwards. And radius, we will take the radius 127 and length, say 2 meters. And with this one, we already have an idea where this cylinder should be located. Yeah. Of course, we have to define which slave nodes should be taken for this crash, for this pole crash. The car will be moved in Y direction towards the pole, and so we will just define the nodes by an ellipse selection. So, for example, we will take all nodes over here, and when we're finished with this definition, we can just save this rigid wall definition again, and we're done. Yeah. In the same way, we can define all other boundary conditions and load cases. For example, boundary conditions, concentrated loads, contacts, gravity load, initial velocities, rigid wall, pressures, and so on. Everything can be defined with a similar panel, and it's very fast, very easy to define, and also the visualization is very nice in this case. Okay, so we've already seen there's also contact definition over here. So in this contact definition, of course, in this panel, we can see all the contact definitions available, and we can define a new one. Let's look at the tight contacts. In this case, some solid part is glued inside of this longitudinals by tight contact definition. We see the red slave nodes and the blue master surfaces. And again, in this visualization, we can see very nicely how this contact is defined. We have again access to all possible parameters, and you see that we also have this optional cards, like optional card A, optional card B, and so on. Let's look at the general contact. It's an automatic single surface contact that's defined for the whole car structure. Of course, the visualization says that everything is master, everything is slave, so the visualization is not very interesting in this case. But we, again, can change all the parameters over here. And in this case, we can do a penetration check for this contact. So I will start the penetration check right now, and we will get a new panel, a penetration check panel, where we can see different intersections and different penetrations in our model. So let's look at the intersections first. There are intersections between part 1 and part 2. We can look at that in detail. So it's just a part in the gearbox over here, and we have the possibility to correct these intersections manually by hand. So, for example, we can use this manual correction tools, move in the plane defined by the neighboring elements. That means I can just take this node and just move this node around as I think that the intersection will be repaired. But I can also use an automatic intersection fix. Yeah, so I can just say remove intersections automatically in this case, and if it's not very difficult to do that, if it's clear for the automatic algorithm how to repair this penetration or this intersection, then it can be done automatically. So then, if we've repaired the intersections, we can do recheck of the penetrations, check the penetrations again, and we see that we have a number of 459 penetrating nodes. We can look at them also again in detail, see what's happening in these areas. So there's a penetration over here, and we can clear this penetration manually again, but also we have an automatic penetration fix in this case, and you see that the node is moved and this penetration is fixed. So we don't have to clear all these penetrations one by one. We can just select all of them and make a so-called automatic depenetration. That means this depenetration is done full automatically and in a recursive way. That means so if we repair one penetration, of course we can get another penetration, but this automatic penetration fix will work recursively. That means it will work with different gaps. It will change the gaps, and it will repair all these penetrations one after the other until all penetrations are gone. We can fix parts in this tool. That means if we know that one of the parts is very new and should not be touched by the penetration fix, then we can fix this part. We can undo the penetration fix. We can undo the depenetration. And there are different visualization tools to work with this penetration tool. Okay, so much for the contact interface, so much for the contact definition. Let me come to another very interesting tool, and a tool that is used quite often in LS-DYNA. It's called include transformation. That means, let's look at the browser again. In this case, we have different include files. And for this include files, for example, we have the wheels over here, isolate with transparency. We can look at the wheels in in detail. I will switch to normal view instead of perspective view, and just look at the car from a side view, a clear side view over here. And in this case, it might be interesting to switch this include file to an include transformation type. Yeah, that means during import of this include file, the include file can be transformed. It can be shifted. The IDs can be updated, and so on. So in this case, we will change the subtype from include to include transformation. Yeah. So here we have now an include transformation, and we can edit this one. Yeah. And in this case, what we can do, we can define an offset for nodes and elements. We can create a new transformation for this include file. And in this case, we can say, okay, we want one new transformation, and this transformation should be a translation, for example. And this translation should be defined, for example, in Z direction by 100 millimeters. Yeah. And as soon as I define and save all of these definitions, then you will see that these wheels will be moved by 100 millimeters. Yeah. And this is a very nice procedure that can be used in LSDyna and can be defined in HyperCrash. It is commonly used when you want to position barriers, for example, or when you want to position dummies or whatever you want. You can just import an include file and then position this include file at the same time with this include transformation statement. It's very common and very nice to use. Okay. Another feature which is very often used in LSDyna is parameter. So what you can do in LSDyna is you can define a parameter and use this parameter at any position within your model. So in HyperCrash, you can use the parameter editor to define this parameter. So in LSDyna tools, you will find the parameter editor. And in this parameter editor, you can define a new parameter, a float parameter, for example. Call it, for example, Young for Young's modulus, and give it the value of 210,000 for the Young's modulus, and save this one. Yeah. You will find it here in the list, and as soon as you've defined this one, you can use it anywhere in your model. For example, if I go to the materials, look at the first material in detail, review this material, and in this case I can just, instead of hard coding this 210,000 value, I can just right click and select a parameter. And here this parameter appears, and I can just type in this parameter, and you see the actual value is displayed over here, and I will save that one. Now, if I change this parameter, if I go in here, change this parameter and say, okay, we have an aluminum part, and save this value over here, go back to the material, go back to this first part, then you see also here the value has changed, and this is because the parameter is used here instead of a hard coding in this place. So this is very nice to to define parameters when you want to create more and more variants of your model and use different values for different parameters. Okay. So finally, when you've defined your whole model, when you've defined all loads and all boundary conditions, when you've defined data history, for example, cross-sections, accelerometers, and so on, when you've defined all control cards in your model, for example, control time step, control energy, and so on. When you've defined your whole model and when you're finished, then at the end you will do a model check. So we have a very nice model checker over here. You can run the model checker and it looks for typical errors that can be defined in an LS-DYNA model. And you see that we have some green signs over here, and these checks are okay. Then we have some orange ones. These are warnings. For example, only one part. That means when we look at that in detail, then we will have a rigid connection that only defines one part. You see this one over here, it's this one. It's only a rigid connection that is just fixed on one part and doesn't fix two parts together. Friction, that means when we look at that one, friction is not well defined in the tight contact that glues these solid parts in the longitudinals. We have some free nodes, so with these free nodes, you can look at them, or you can do an automatic correction. Automatic correction in this case means delete the free nodes, and as soon as we've deleted them, this error or this warning will disappear. Some mandatory fields are missing. We can look at that in detail, or we can do a correction, and in this case the correction says it's not possible to do that automatically. We have to define the missing fields manually, and we will go into this mud crushable foam part, and we can define the missing value over here. So this model checker is very nice, and usually when all errors are repaired, then the model will start immediately without any problem. Okay, so let me show you some more interesting definitions over here. Mass part details is very important. You will get an overview of the mass for all parts, and a lot of care has been taken that you see exactly the same mass that you will find in the D3HSP file from LS-DYNA. There are different ways to add mass, to distribute mass with non-structural mass, nodal masses, constrained nodes, rigids, where mass is distributed to different parts. So care has been taken that you see the total mass of every single part, the part mass, the structural mass, and also the lump mass, which is added over here. And of course, now you can give, in this case, a target mass if you like, and it's possible to match the target mass and to add extra mass in order to get the target mass that can be defined over here. All other tools can be found either in load case or in the LS-DYNA tools. You see some hourglass functions over here. Friction can be defined. Again, transformations over here, ALE, damping, and so on. And you see some more information down here, pretensioner, retractor. These are tools for safety and belt modeling. We will come to that now in the next section. So the next section will be all about safety, safety tools, dummy positioner, seat deformer, and belt generator. I would like to show that in detail now on a different model. So let me open this this different model. This is not the correct one. It's this safety model over here. So this is just a seat structure over here. We have a B-pillar with some belt structure. We have the floor down here. And now if we want to import a dummy and position this dummy, we just go into the dummy positioner. We can import a new dummy over here. We can have a whole database for dummies where we find the different dummies by a norm, by a person, by a percentile, by modeling, rigid, fine mesh, and so on. In our case, in the demo now, we will just open it from the file. H350 dummy will be imported, and we get a small picture where we can see a preview of the dummy and see if this is the correct one that we want to have. We validate this one and can give an offset value, if you like, for the dummy. And as soon as we import this dummy, we can see it in the graphic display over here. Of course, now we want to place this dummy onto the seat at some special position that depends on the R point, on the H point. And the first thing that we can do, we can define the position for this H point either by node position or by coordinates. We can say, okay, the X position is somewhere around here. The Y position is also somewhere around here, and also the Z position. If we want to make the definition, if we know the exact position of the H point, we can import a file with the exact position, and then this is done very exact in this case. Now, after position of the H point, we can go for the different joints and jokes that we have. We can position the joke on the right side by simply selecting the angle that we want to change and then just moving it on the screen. Yeah. We also have stop angles, and you see I can't move it further than these stop angles are allowed. And when I'm finished with that, with this positioning of this joint, then I can choose another one. Again, choose the theta angle that can be changed here, and position this limb wherever I like. Head and neck, for example, choose another angle and move this angle a little bit up and down. Yeah. Okay, and that's it. You see primer tree file, so HyperCrash understands the standard primer structure for defining the body of dummies. And after you've defined the dummy position, you can close this dummy positioning tool, and we go on to the belt generation. So belt generation can also be done in HyperCrash. So you see belt generator over here. We can define a new belt, give it a name, and define it with 3 points, for example, on the seat and on the dummy. I will switch off all the solid parts in order to choose the nodes only on the synthetic shell parts. Choose 3 nodes, for example, down here on the seat part, here on the dummy part, and again on this seat part, belt part over here. We can define the parts where the belt should go, for example here and here. You can define the gap, the width of the belt, the element size. You can define the material and property and make a preview for that. And you see that the belt looks quite well, and it's defined very nicely on the surface of the dummy. If you've forgotten some parts over here, no problem. You can just add another part to your selection, make another preview, and the belt will fit to this part also. Yeah, you can save this part, and the belt is defined as you've chosen the nodes and the parts where the belt should be lying. Okay, another tool for positioning the dummy within the seat structure, within the seat foam over here, is the so-called seat deformer. Usually you will use simulation to put the dummy into the seat foam. In this case, you can use the seat deformer to morph the seat foam according to the shape of the dummy. So let me show you how this works. So in our case, we will just position the dummy as seen in this picture. So X direction is in front and Z is up. So as in our case, so this is the first step out of 5 that we have to define. Next step will be select seat parts. We have to define which parts are the seat foam. So it's this part and also this part up here, except this one. Then we have to define the dummy parts. Again, it's better to only use the synthetic shell parts instead of the solid parts. So I will just switch off all the solid parts and just choose the synthetic parts. For example, this one over here. Then somewhere here, up here, this part, and that should be enough for the moment. Except this step, then select back seat nodes by part. That means again we have to define which foam part is on the back seat. And finally, we have to decide which nodes are fixed and which nodes are allowed to be moved. That means we can either do an automatic selection, then all nodes on the back and down here are selected, or we can do it manually if we, for example, allow the seat foam to be moved a little bit through this area. So for the demo, I will just switch auto and accept also this step. And now HyperCrash will do morphing of the foam parts with respect to the shape of the dummy. You see over here, we can also define, ask HyperCrash to generate a reference state. That means the pre-stresses will be defined by the difference of the original shape of the foam parts and the morphed shape of the foam parts, and this allows to incorporate also the pre-stresses. So morphing is done. I will just switch off these parts and switch the whole display, and we see that morphing took place in these areas and also down in these areas. Yeah, very nicely. Okay, so that's it for the safety tools, and simulation can start with a dummy sitting inside your model, and you can you can export the LS-Dyna model right away and start the simulation. What else can we say about HyperCrash? This was a short overview. Let me give you just one slide for the positioning of HyperCrash within the whole HyperWorks tool or the HyperWorks suite. We usually use HyperMesh for meshing. As a meshing tool, and then for assembling parts. Of course, you can also define all boundary conditions and load cases within HyperMesh. But as you've seen, it's very easy to do that in HyperCrash, and it's very easy to also do all the safety, use the safety tools to do the positioning of the dummy, to do belt routing and so on. There are very nice tools in HyperCrash, and it's very easy to learn HyperCrash and to use HyperCrash for LS-Dyna models. Of course, HyperMesh and HyperCrash should work together, and let me show you how the future will look like. So this is a beta version of HyperCrash. It will be available soon with an update of HyperCrash 11.0. And this update includes the combination of HyperMesh and HyperCrash. So what does that mean? So as you know, HyperCrash is not able to do meshing. And now if we want to do some kind of remeshing, for example, for this window over here, then we can just look at this window and say, okay, I want to do mesh editing in HyperMesh. So we can say, okay, I want to transfer this selection to HyperMesh, and then HyperMesh will start immediately. And within HyperMesh, you can do all the operations that you know and that you want to do on this part. So, for example, just delete some parts over here, some elements over here. And now, as soon as I close HyperMesh now, I will be asked if I want to transfer all elements, or a selection. In this case, we say we want to transfer all elements. And as soon as I save this this operation that I've done over here, then we will also find this changed part, the missing elements within HyperCrash. So you can use HyperMesh and HyperCrash in conjunction. You can use HyperMesh for mesh editing, changing some parts, changing some elements within your model, and then come back to HyperCrash with this changed part. You see HyperMesh batch file. You can also run TCL scripts. You can run a HyperMesh command file. You can do all the operations, all your TCL files that you have created for HyperMesh. You can use that within HyperCrash, running HyperMesh in batch mode. Another possibility over here, import mesh from CRD. That means you can just choose a CRD file, and during import, the batch mesher will just do the meshing of the CRD part, and you can work with the meshed part in HyperCrash. So that's a new version of HyperCrash that will come up in the near future. beta version is also working fine, and I hope we will have that in the next update for HyperCrash. So that's the end of this small overview of important new features in the interface for LS-DYNA. HyperCrash is able to build up LS-DYNA models very fast and easy. You have access to all well-known features within LS-DYNA. You can define all features and functions that you know in LS-DYNA, and you can also convert models. That means in this case, if I import a radius model, you can convert. It will be converted automatically to LS-DYNA. Also, Nastran models will be converted to LS-DYNA, and also the other way around if we want to test that. So I would like to say thank you for your attention. If you have questions, please don't hesitate to ask us. We can help you to set up your model and to make the first steps within HyperCrash. Thank you very much.